Friends, let's have a look at problem 2936, number of equal numbers blocks. In this video, our main purpose is to practice the use of binary search. And we are going to use this example as a specific use case and present 3 different ways of binary search. Our plan will be the following. First, we are going to digest the problem requirements, and then we do the analysis, and finally, we share the 3 formats of binary search. First, let's look at the problem statement. So here, we are given a zero-indexed array of integers called nums. So the following property holds for sums. So all occurrences of a value are adjacent, right? So this is very simple to understand, but here I use some mathematical symbols or statement to demonstrate this one, to make it rigorous. So since nums is a very large array, we are given an instance of class big array, which has the following 2 methods. So one is add. So for this function can help us retrieve a value at a certain index. And this one is not correct. If you look at the class definition here, so the size method actually gives us a integer, which is the length of this array. So we want to partition the array into maximal blocks such that each block contains equal elements. So we want to return the number of blocks. So note that if we want to test our solution using a custom test, behavior for test with a num has a length greater than 10 is undefined. So here are 3 examples. So the third one is very special because each element are different and they appear just once. So therefore, the blocks are 7 in this one. And in the first one, so all the elements are the same. So there's only 1 block, so we return 1. So the example 2 is a demo of general case. So here we have 3 ones. This is the 1 block. We have 1, 3. This is another block. We have 3 9s, another block, and 2, another block, and 2 10s, another block. In other words, we want to find the number of unique values in this long array. So in this example, that is 5, right? So it's important to notice the constraint, especially this one. So the length of these nums can be as long as 10 to the power 15. So in other words, we cannot use a linear scan, right? So also, the nums is in between 1 and 10 to the power 9. So if all the elements are not the same, so 10 to the power 9 is also very large. So we can still not use linear scan. So with that said, we are ready to look at the logic or the method we are going to take. So as we have pointed out, we are going to practice the use of binary search. So actually, binary search is a very simple algorithm, but it can be very sophisticated. It can be very deep. So here, our plan is to write 3 different formats of binary search. Hopefully, this will help you get a better understanding of the idea of this method. And actually, most of the case, so if we want to use binary search, we need to use it specific to the use case, right? But there are some general rules. It's good to have a feeling, but overall, you need to adapt the method to the problem. So with that said, basically, I want to mention that we are going to focus on search range shrinkage and boundary conditions in this video, right? So with that said, let's look at the coding part. So here I want to write our first solution. First, I'm going to get the nums size. So this method gives the length, right? You can think of this n as a large number. So not the same length as the given examples. They're very small in length. So with that said, we are ready to do something like this. First, for an index L. So we want to find the max R, the right index, such that nums R is still equal to nums L. So here we see nums r and nums l. We can understand like this: nums r equals nums at l. But we need to change the bracket to be parentheses, right? So this is due to a specific problem, and this function can be easily write. So here I'm going to write it as a just a function f. So give me an index. I want to find the rightmost index in the array such that that still equals the element at index left. So in other words, here in example 1, so given 3 at index 0, the rightmost index will be 4, right? Similarly for here, given 0, right, the rightmost will be 2. If you're given 3, it will be the same. And I give you 9, so this is the 4, right? So the rightmost will be 6. That's what we want to write. So this is actually very simple, but though, you know, in this long list, there's no order relation, but we can use the idea of binary search. So first, let's freeze on the value, nums at left. So this is the value we want to examine. So now we specify the left window, left pointer, and the right pointer for binary search. See here, rigorously is not a binary search, but a search space shrinkage. So we are going to have r left equals left, r equals n minus 1. So here we have make n, so sort of global. We compare the scope of this function, right? So now what we want to do, so we want to write L. So here in this version, I'm going to write L strictly less than R, right? So you can imagine if the big array contains more than one element, if R is very large, so this will be different from the left, right? So you can think of left and to be 0 at the very beginning. So I'm going to write a middle. So I'm going to shrink from the right to the left. So R minus L, integer division by 2, right? So now the condition we are going to check is nums at mid. So if it equals value, so this means that mid is, we can consider if we can push to the right further. So in this case, we can set L to be mid. In other words, L always make this condition holds, right? So now otherwise, so if nums at mid does not equal to value, and then what we do, we can do R equals mid minus 1. Notice that at index mid in the else block, they are not equal, right? So we set R equals mid minus 1. As we mentioned, after the val block, so we see that L, this index in this writing logic, L always make this condition holds, right? So we are going to return L. So this is our main function. So now if we want to find the number of unique elements, that's very simple. Let's initialize a result variable. This is a counting variable. And the current index, we're starting from 0, right? Then let's use a val block. Val current is less than n, the size of the big array. Then we can do a search to search the rightmost index corresponding to the element value at current. So this will be f current, right? And then we're going to, once we do such a search, we're going to increment the result by 1. And next time, we're going to set current equals idx plus 1. So consider next element, right? So afterwards, we just need to return the result. This is the one version of solution, right? So now let's do a test. Yeah, it passes example 2. Now let's look at the generic case. It runs slow, but it passes. Now let's quickly analyze the time complexity. So this is very simple, right? So here we can assume that the unit time is the time we look at this at operation, right? The unit time. So it's to be the time for at method. Then we want to see here in this one from left to n. So we do sort of binary search. So the temp complexity will be n logarithm n. So let's see, it's n minus roughly the size, right? If you like add 1, so is this the one, right? So then here actually depends on how many unique elements we have. Basically, each time we are going to call this function f using this temp complexity. But it's basically so you have left 1, right? And then you do something like n logarithm, so n minus left 2 and plus so n logarithm, so n minus L3 log Lk, right? If assume that you have k unique elements, so then basically you can do something like this: logarithm n minus L1. L1 can be 0 at the very beginning, right? So this logarithm n minus L2, and then plus logarithm n minus Lk. Let's assume we have k non-unique values. So roughly, this is the k terms, right? K log times logarithm n, then times a linear temp complexity. So here we do this computation up to a constant, right? So here, I guess for our purpose, I don't want to analyze further, right? So actually, this is not very efficient. The reason is that this n can be very large, but this provides one solution. So this actually, let me make another comment. So typically, another use cases for binary search, so like general paradigm, so is 2 steps. You define Boolean function to produce order or monotonicity, and then you do search range shrinkage. So you can see the binary search playlist in our channel to get more practices or more similar problem using this general paradigm. So in this one here, we just focus on basically search range shrinkage, because that's so simple in logic. This is the one solution format. Here I want to mention here. So here is strict inequality, right? So here, that's why I write here mid minus 1, but here I write mid. So this 2 here and here is in correspondence. So this is the one solution. So now let me copy this part. Let me write another one. So let's call this one solution V1. And for this one, I still write a solution, same complexity, temp complexity as above, and then we can move to the third one. So for the second one, I want to still write a binary search solution, but I want to use a less than equal in this condition or boundary condition in the while block. So here let's write a total. That's the result, right? And the ID x and n. So originally the total is 0, and we start from 0, and n is a nums size. So notice that here we call this a size method for the big query. Next, we want to do binary search, but we write this one in a different format. So ID x less than n. So in this case, we still expect we have more unique elements. Then we can see first we similarly as above, we freeze the value. Right? Then we have a low and we have a high, same like L and R. So the value we freeze is nums at this index, right? We freeze here, and the left will be same as index, right will be n-1. Then we do sort of binary search. This is not a binary search in a rigorous sense, but binary search range shrinkage, I would say. So now it's a val block, val low. So here I would write less than or equal to high, right? So in other words, if low and high are the same index, for example, you have example 3, you have a 3, or example 2, you have a 3 here. We just need to do one operation. So what we want to do is that we check mid. So we do not do shrinkage from a direction like here, right? From high to low, but here we do it in a symmetric way. So low plus high over 2. So this way it makes the shrinkage symmetric. In the rigorous sense, the shrinkage is not symmetric in this problem. We just want to move to one direction, right? But this is a little bit deeper, but it's good to grasp the difference. So now let's check if nums at, so let's check middle, right? If it equals value. So what we want to do, in this case, it means that, this way, we can still push to the right. So we can set low equals mid plus 1, right? Otherwise, they're already not equal. So we should set high equals mid minus 1. So this is basically our one round of while loop. After this, you will see you can expect high is less than low, right? So then what we want to do, the stop condition for this will be high minus 1. So here, once we do one search range shrinkage, so we're going to increment the total by 1. Then we set next index will be high plus 1. So this will always be right? Because later high is less than low, but then we make it plus 1. So this index will correspond to next unique elements. And then what we want to do is to return the total, right? So compared to the first version, I feel that this version is more compact, while the first version is more modularized. So now let's do a test. Yeah, it passes one example. Now let's look at the generic case. It's running slow, but it will pass for current time. Yeah, so this is the second solution format. So now let me copy this part again. So let's write the third one. So I'm going to change this one to be version v2. So now for the third one, I want to make it more adapted to the current problem. So what I want to do is, first, I'm going to write a function, basically check, let's see, helper. So given 2 index, so I'm also given 2 values. So the big array is as in this assumption of this problem. So what we want to do is given 2 values in this array, we want to find the number of unique elements in between I and j, both inclusive. So that's our purpose. For this, actually, it's very simple to do, because the main assumption for this problem is the following. So now, so here, all occurrences of a value are adjacent, right? So now let's see if value 1 equals value 2. So then we just return 1, right? Just one non-unique unique values. And then we want to check another stop condition or base case for recursion. If I is greater than or equal to j minus 1, or in other words, if I plus 1 is greater than or equal to j. So in this case, because we assume value 1 does not equal value 2, so in this case, so we're going to return 2, right? Because there's only 2 numbers, and then the value 1 and value 2 are different, so we have 2 unique values. And then the generic case. So this is very simple, right? So I'm going to write k equals I plus j over 2, right? And then the temp, I'm going to call it nums at k, right? So we compare this value temp with value 1 and value 2, right? So if temp equals value 1, it means that from index I to index J, it does not give us new values. We just need to return, in this case, helper from K to J, value 1, value 2, right? Another case is if temp equals value 2. So in this case, we know that from K to index J, it does not provide us new values. So in this case, we just need to return helper I to K, value 1, value 2. So then the generic case, we know the temp is different from value 1 and value 2. This actually gives us a new unique value. So in this case, so we're going to return helper I, K, value 1, and temp, right? And then helper from K to J, temp, and value 2, right? But we need to minus 1 because in these two functions, we both count the temp. So we count it twice, so we minus 1. So this is our main function, right? So in this one, we didn't do the binary search in a very verbose way like this, from some index then up to the end, from index up to the end, right? So I would say this is not n method, so this is the n L1 times so n L2 times, and similarly n minus LK. So in other words, the binary search is the binary operation is n logarithm n, where n will be the search range span or length. So for this one, we just use once. So now let's do this. So let's write the main return. So let's first get the size of this one, and then what we want to do is to return the hyperfunction. So starting from index 0 and index 1, and nums at index 0, and nums at index n-1. So if you like, you can write it more confined with the Python format. So with that said, I guess this is the third version. Let's do a test. Yeah, it passes one example. So this solution is much efficient than the first two. Let's submit. Yeah, it passes all the cases. So roughly you can run several times and compare the runtime, this one and the previous one. So with that said, I guess that's basically the main content for this video. As we mentioned in this video, we present 3 formats of binary search solutions. Hopefully this will help our members to understand or help us to further think of the binary search. So with that said, I guess that's it for this video. Thank you.